Well, now we have already simulated the Gaussian white noise and Poisson white noise. Now, since they are IID observations, they are white noise, so their plot should be, their autocorrelation should be 0. It must be around 0. So at lag 0, they are 1, but after that they are within the limit. So autocorrelation does not cross the upper limit and lower limit. Similarly, here partial autocorrelation is also in the same range. ACF. No, this is the ACF, autocorrelation function of, this is the Gaussian white noise and this is the Poisson white noise. It is clear from this. ACF for the simulated Gaussian left and Poisson right, where noise shown in the figure. Interestingly, the RK are all greater than 0 in absolute value, although they are not statistically different from 0. For lags 1 is to 20, they are not significantly different from 0. For the lags 1 is to 20 in both the cases. Now, I am going to talk about random walk. Random walk receives considerable attention in the time series analysis because of their ability to fit a wide range of data despite their surprising simplicity. In fact, random walks are the most simple non-stationary time series model. So, random walk is a non-stationary time series model. A non-stationary means it is not white noise, it is having some trend. A random walk is a time series xt where xt is equal to xt minus 1 plus wt, and wt is a discrete white noise series where all values are independent and identically distributed IID with mean 0. In practice, we will almost always assume that Wt is a Gaussian white noise such that Wt is normal 0q. We will see later that random walk is a special case of autoregressive model. Simulating random walk. See, set.seed, set a number, a random number seed, set.seed 1, 2, 3, length of the time series Tt is equal to 100, then initialize xt and wt. So, xt and wt we are initializing is equal to r norm n is equal to 100, mean is equal to 0 and sd is equal to 1. Then compute 2 through tt for t in 2 to tt because this is the first observation, and from second to 100th it is generated by this process. Xt is equal to xt minus 1 plus wt, xt minus 1 plus wt. Let us plot the simulated time series in ACF. So, par mf rho is equal to, so this is the plot.ts and y lab is equal to expression italic xt. Actually, here expression means we want to write mathematical expression and it is xt, x italic, it should be italic, x should be italic, and t here it is the subscript in graphics. It works as subscript. So, ACF. So, this is the xt, this is italic xt, and this is in the subscript. So it is the mathematical expression when we want to type here. So we write expression italic and ACF plot. This is the time series plot and this is the ACF plot. You know, here it is not stationary. It is highly correlated data. Perhaps not surprisingly based on their names, autoregressive models such as random walk have a high degree of autocorrelation out to long lags. See, even up to the lag 10, 11, it is highly correlated. It is highly correlated. Alternative formulation of random walk. Alternatively, we can derive the result of random walk and we can simulate using R functions cum sum. As an aside, let us use an alternative formulation of a random walk moved to see an even shorter way to simulate random walk in R based on the definition of a random walk in equation. It is easy to see that xt is equal to xt minus 1 plus wt, but this xt minus 1 can be written as xt minus 2 plus wt minus 1. Then, therefore, if we substitute xt minus 2 plus wt minus 1 here for xt minus 1 in the first equation and then xt minus 3 plus wt minus 3 t minus 2 again and so on in a recursive manner, we get xt is equal to wt plus wt minus 1 plus wt minus 2 plus wt infinity wt infinity. In practice, however, the time series will not start at an infinite time ago, but rather at some t is equal to 1, in which case we can write xt is equal to w1 plus w2 wt. So that is nothing but the cumulative sum of, that is the summation t is equal to 1 to t wt. So it is easy to see that the value of random walk process at the time step t returns sum of all random errors up through time t. So here we will write cum sum. Therefore, in R we can easily simulate a realization from a random walk process using cum sum function of x, which does cumulative summation of the vector x over its entire length. If we use same errors as before, we should get the same result. So x2 is equal to cum sum ww. So here let us plot the graph. Here this was earlier generated by the command and this graph was generated using cum sum, and both are having the random walk, both are non-stationary and their behavior is same. The two plots generated by the two methods of simulation are in close agreement. So they are of the same type. Simulation, so we can go into, see here, we can generate ACF CO2. So this is a highly correlated data, autocorrelation function, and then Here we are having these things in fraction. So to avoid that, we have to write as dot numeric CO2. So it is giving the same result, but with as dot numeric it is giving 0 to 36. Partial autocorrelation we have already defined, and PAC of CO2 log max is equal to 36. So this is the partial autocorrelation function of CO2 observations. Then as dot numeric gives this result up to 36. White noise, C, set dot seed, Gaussian white noise, GWN is equal to R norm. R norm always generates random sample, and that is nothing but they are IID samples. Similarly, Poisson, R Poise, it also simulates observations from uncorrelated observations from Poisson distribution. So we can run and we can get their plot also. So to get the plots, so these are around 0 both the sides. Here it is around 2 both the sides. So this seems to be a white noise process. Then there ACF of both are not autocorrelated because they are following the white noise price. Interestingly, ठीक है, random walk, we are simulating random walk, simulating a random walk, set dot seed, length of the time series TT is equal to 100, then initialize XT and WT, XX is equal to C. If you run this, and then C XX it is assigning some random number, and then we are here actually generating T into to TT, and it is XT is equal to XT minus 1 plus WT. So it is random walk. So here it is random walk. Now we can get XX or we can get WW. Why it is? Yes, it is saved in the object. And then we can have the plot.ts. So these are the observations which are being simulated, and this is the ACF plot of random walk. This expression XT italic, it is italic, and XT if you write in the square bracket it will be termed as subscript. So this is the time series plot and this is the ACF plot. Then alternative formulation of random walk. See what we have done. We have used on WW, we have used cum sum, cumulative sum. So now X2 is the cumulative sum. So plot of X2 and plot of XX should be same. Because plot.ts access ylab is equal to expression xt, ylab is equal to expression st. So this is the x is the object which is generated by this process, random walk, this method. And this one, cum sum methods, is also being implemented on x2. So both x and x2, they are random walk. They are generated by the random walk process and they are generated by the equivalent here cum sum ww. So we are having these same plots. So both are random walk. Both are random walk, but they are generated by the different processes. They are generated by the different processes, but random walks, this time series plot is giving the same result. It is almost similar results. So this we were trying to confirm that the result of in both the methods generating a random walk time series appear to be equivalent. So these two we are generated by the two methods, but they are very similar, they are equivalent method. Now we shall talk about simulation of time series data arima.sim, and that we will talk in my next lecture. Tomorrow's lecture I will talk about arima.sim. Arima.sim actually it is help arima.sim see it is in the stats package. Simulate from an arima model. Simulate from an arima model. Description. So arima.sim. So this is the help which is available with the stats package. Here we can talk about simulation from a time series arima.sim. The function, I would like to read these things from my simulation from a time series arima.sim. The function arima.sim works for all forms and subsequent and subsets of arima models in R. Arima.sim will accept many arguments, but we will be interested primarily the three of them, namely n, the length of the desired series, model, a list of the following order, a vector of length 3 containing arima p, d, q. So this is the order p of AR model. This is the order q of MA model, moving average model, and this is the difference. So SD, the standard deviation of Gaussian error. So these are the simulation from ARP model. Mathematically, an ARP means ARP stands for auto-regressive model of order P. So this is the model definition. Xt is equal to phi 1 xt minus 1 plus phi 2 xt minus 2 phi p xt minus p plus wt. So this is the model for ARP. Let us begin by simulating some AR1 model. AR1 means up to this stage only. So xt is equal to phi 1 xt minus 1 plus wt, AR1 model. And comparing their behavior, first let us choose model with contrasting AR coefficients, with contrasting AR coefficients. So AR coefficients phi 1 one time positive, another time it may be one time is small AR1 AR phi 1 means AR, and then phi 2 AR is point, not phi 2, it is another choice for phi 1. That is, here we are having a small AR, here larger AR, because they should be chosen between the range of -1 to +1 to generate a stationary series. So I would talk on these things in my tomorrow's lecture.